If you're new to competition math, the AMC8 can feel like a whole new dimension, but you have come to the right place. The Mastering AMC8 book and video series comprehensively covers all of the important concepts that you need to learn for the AMC8 and other math competitions like Math Counts. The AMC8 contest includes many interesting problems from topics like permutations, combinations, recursion, telescoping, modular arithmetic, and 3D geometry, along with many other concepts. But unfortunately, most school curriculums don't cover these topics. This book and video series will be your guide as you explore the amazing world of competition math. Let's get started with permutations, but let me first become small. So what is a permutation? A permutation is an arrangement where the order matters. So for example, if you have 3 pencils in a line, that's a permutation because they have an order. Okay, another important concept, factorials. So for math competitions, it's recommended that you know factorials and some common ones. So a factorial and factorial is just the product of n times n minus 1 all the way till 1. Basically, all the numbers that are between 1 and the number itself. You take the product of it. For example, 4 factorial is just 4 times 3 times 2 times 1. 2 factorial is just 2 times 1. 3 factorial is 3 times 2 times 1. And this is true for any number. 1, 2, 3, even 100. And there's also another interesting one, 0 factorial. And this is the one that some people often get confused with. 0 factorial is 1. And this is just an exception that you have to know. Okay. Let's take an example that uses permutations and factorials. There are 4 different AMC8 videos. Every student in the class watches the videos in a different order. What is the maximum number of students in the class? So every student is watching the 4 videos. Let's call them A, B, C, and D. So there's video A, video B, video C, and video D. And every student is watching these 4 videos in a different order. And we're asked to find the maximum number of students that are possible in the class. So first of all, if you want to do this, how many orders are there for the 4 videos to be watched in? So let's say that we're watching the 4 videos in different orders, right? So let's say that this first blank is the first video we're going to watch. The video we watch first. Over here is the second video we'll watch. Here is the third video we're going to watch. And the fourth and final video we watch will be over here. So we have like 4 blanks here. Right? Okay, so the first video. We could try listing out all possible combinations. So A, B, C, D. B, A, D, C. C, D, B, A. There's a ton. The point is, it's going to take a long time for that to happen. So maybe let's consider them choice by choice. How many choices do we have for the first digit? How many choices of videos to watch? We have 4 choices. A, B, C, or D. There's 4 videos that we could potentially watch for the first video we're going to watch. So there's 4 choices over here. Now let's just say that we picked A as a video. Now we could pick anything else. We don't have to just pick A. We could pick B, C, or D as well. But it doesn't really matter which video we pick because there'll still be 3 videos left regardless. So there's going to be 3 choices for the second video, no matter what we picked as our first video. And let's just say we picked D as our second video, right? So A, then D. So just like I said earlier, it doesn't matter which video we pick, because there's going to be 2 choices left for the third video no matter what. Times 2. And let's just say we pick B. Finally, no matter what 3 videos we chose earlier, there's just going to be 1 video left, and that's going to be, in this case, C. But no matter what, 1 choice. So the number of choices is just 4 times 3 times 2 times 1. Look familiar? Well, this is 4 factorial. And if you memorized your factorials, you would know that this is 24. Okay, so there's 24 different possible orders for the videos to be watched in. But then what is the maximum number of students in the class? So every student in the class watches them in a different order, right? So there's no way we have more than 24 students in the class. Because if you had something like 30 students, then there would be some students who watch the video. There would be some students who watch this, who have the same order they watch the videos in. So the maximum number of students in the class is just 24. All 24 possible ways to watch the 4 videos in, each one corresponds to 1 student. So each way to watch the videos in, that's 1 student. So at most we can have 24 ways. And anything larger than that will result in 2 students having the same order they watch the videos in, which is not allowed. So our answer is just 24. A really interesting problem that uses factorials and permutations. So this formula I use here, the number of ways of arranging n distinct objects is n factorial always. So for example, you know how I found that to watch 4 different videos, it was 4 factorial. Now this is not just true for 4. If we had 6 videos, then there would be 6 factorial ways to find an order to watch them in. And we can arrange objects. For example, we could be arranging 6 pencils on a table. That would be 6 factorial, right? Or 10, even for larger numbers like 10, 20, whatever. Any number n, the number of ways to arrange it, n factorial. Okay, let's try another interesting example. Sam has 5 different stamps and is making a Christmas card where he puts 3 different stamps in a line. How many different Christmas card designs can he make using the stamps? So we've got 5 different stamps. Let's just call them stamp A, stamp A, stamp B, stamp C, stamp D, and stamp E. So these are our 5 stamps. And Sam wants to put 3 of them in a line. So let's say this is the card. We're wanting to put 3 of them in a line. So there could be a stamp here, and then a stamp here. So we're asking how many different Christmas card designs can he make? So using these stamps, he must put them in a line, and we're asking how many different such designs are even possible. So, just like earlier, in the previous example, let's take it stamp by stamp. So for the stamp that's leftmost, so for this stamp over here, the leftmost stamp, how many choices do we have? Well, we can pick any one of these 5 stamps. So there's just going to be 5 choices. And let's say we pick stamp B. It does not matter which stamp we pick for this choice, because no matter what, there's going to be 4 stamps left. And the problem says 3 different stamps in a line. So if this stamp is B, this next stamp can't also be B. It has to be something different. So no matter which stamp we pick for the first leftmost stamp, there's going to be 4 stamps left. So there's going to be 4 choices for the second stamp. And finally, for the third stamp, let's just say we pick D for the second stamp. So B, then D. Now there's going to be 3 choices left for the third stamp. So 3 choices left for the third stamp, right? And this is true no matter which stamps we picked earlier. It doesn't matter which stamps we pick, because no matter what, well, after we're picking 2 stamps for the first two boxes, there's 3 left, so 3 choices for the final stamp. And maybe it's something like C. It could be anything though. BDC, that's an example. And we found that 5 times 4 times 3, because 5 choices for the first stamp, 4 for the second, and 3 for the third. That's 60. So Sam can make 60 different Christmas card designs. Now let's explore the permutations formula. So what we just explored is an application of that formula. So I know this might look a little scary, but it's just basically what we did, just generalized. So essentially what this is saying is that the number of ways to order k objects out of n total objects is just n times n minus 1 times n minus 2, all the way till n minus k minus 1. It's essentially what we did here. We had 5 choices for the first one, where 5 was n, then 4 choices for the second one, then 3 for the third, because we were picking 3 stamps. So this is just a generalization. Essentially, the key idea is to consider for each choice how many different choices for each object, how many different positions do we have. Like here, we had 5 choices for the first position, 4 for the second, and 3 for the third. And in this case, it's just a generalization. N choices for the first one, then n minus 1 choices for the second one we pick, then n minus 2 for the third one we pick, all the way till the kth object we pick, n minus brackets k minus 1. And using our factorial notation, we can simplify it to this over here, n factorial over n minus k factorial. So for example, something like 6p3 would just be 6 factorial over 6 minus 3 factorial, which is 6 factorial over 3 factorial, because 6 minus 3 is 3. And we can write this out, 6 times 5 times 4 times 3 times 2 times 1, and 3 times 2 times 1. Notice how these terms cancel. So we're just left with 6 times 5 times 4, which is 120. So that's an example of how to use it. And you can find these explanations. I try to make it so that there's more than just solutions. I'm explaining the thought process behind them. But you can find all of these in the free book, link in the description. Let's try another cool example, permutation. How many 5-digit palindromes are there? So a palindrome is a number that reads the same forward and backward. For example, 14741 is a palindrome, because if we read it from left to right, it's 14741. If we read it from right to left, it's 14741. The same. So that's a palindrome. But something like this, 13235, is not a palindrome, because 13235 is different from 53231. So what must be true for the number to be a palindrome? Well, for it to read the same forward and backward, the first digit and last digit must be equal, right? The first digit must be equal to the last digit. Otherwise, it won't be the same reading it from left to right or from right to left. So if we have a 5-digit palindrome, let me draw 5 digits. The first and the last ones must be the same. Now, the second and fourth ones must also be the same, because if you read it from left to right, then this number will be second, but if you read it from right to left, then this number will be second, so they have to be equal. So first and fifth digit equal, second and fourth digit equal, and the third digit can be anything, because it's always in the third position when read from left to right or right to left. So these two numbers, let's just call them A, are going to be the same. These two numbers are going to be the same, let's say B, and the middle number, let's say C, is going to be does not necessarily have to be the same as anything else. So how many choices do we have for a number like this? Well, the first digit has to be a digit. So it can be anything from 0 to 9, right? No, because the first digit of a number cannot be 0. So 0 to 9, these are all the digits, right? But it can't be 0, because you can't have a number like 04741. That's not a 5-digit number, because that can't start with a 0. So we've got 9 choices for this first digit. Now, what about the last digit? Well, let's say we picked a 4, for example. Well, the first and last digits have to be the same. So the last digit has only one choice. It just has to be the same as the first digit that we already chose. Okay, so how many choices do we have for the second digit? The second digit must be a number from 0 to 9 again, right? So there's 10 choices this time. It can be a 0 because it's not the first digit. And what about the fourth digit? The fourth digit will only have one choice. Why? Because it has to be the same as the second digit. Now what about the third digit? The third digit can be anything from 0 to 9 again. So again, 10 choices. So overall, there's just 9 times 10 times 10 choices equals 900. So 900 is our answer. There's 900 5-digit palindromes. Let's try a little bit more interesting example. How many 6-digit numbers exist such that all the digits are distinct? So 6 digits. And its first 2 digits are 6 or more, and the last 2 digits are 5 or less. And the third digit is a non-zero multiple of 7. Seems like a lot. There's this condition and that condition and this condition. The trick for these types of problems is to focus on the most restrictive conditions first. There's a bunch of conditions, but which ones restrict you the most? Which ones have the fewest number of possibilities? The reason we want to focus on those first is that those are the ones that have very few cases. So then we'll have only a few cases to check at the most. So in this case, what is the most restrictive condition? The first 2 digits, 6 or more. So maybe 6, 7, 8, or 9. 6, 7, 8, or 9. Last 2 digits, 5 or less. So 5, 4, 3, 2, 1, 0. 5, 4, 3, 2, 1, 0. The third digit must be a non-zero multiple of 7. So what are the multiples of 7? 0, 7, 14, etc. But it's a digit, it's not a number. So it's not a big number. It must be from 0 to 9. 14 onwards are too big. And it says non-zero, so not 0. The only choice for the third digit is, well, 7. So that's the most restrictive condition because, well, we only have one choice. So one choice over here. Okay, so now what? How many choices for the first digit now? Well, the first digit, well, okay. All the digits are distinct. So we can't have 7 again, right? So we can't have 7. Then we've got 3 choices left. So 3 choices over here. 3 choices. And it can be anything. Maybe any one of 6, 8, or 9. Let's say it's 8. Let's just say it's 8. Okay. Okay, now what about the second digit? The second digit, it's also from 6 to 9, but it can't be 7, of course, and it can't be the number that was chosen in the first digit. We chose 8, and it could be 8. So no matter what, we can't have 7 or 8. We've got 2 choices. So 2 choices. And let's say we pick 9 over here. It can be anything, but it won't really matter because it won't really matter in our problem here. Now, next, should we look at the middle digit or these 2 digits over here? The strategy you always want to use, look at the most restrictive conditions first. Which one is more restrictive? This digit, which can be anything, or these 2 digits, which must be from 0 to 5. Of course, the digits that must be from 0 to 5. How many choices are there for this digit? It's just 6. But you might be thinking, oh, what if it's the same as another digit? What if not all the digits are distinct? Well, this digit is from 0 to 5, and all the digits we've chosen so far have been 6 or more. So there's no way there's no way we're going to be choosing a number that was already chosen. So we've got 6 choices over here. Let's just say we pick 4 as our number. Of course, we can pick anything. Now, for the final digit, 5th digit, how many choices? It can't be 4, and there's nothing else that it can't be because all the other numbers were 6 or more. We've got 4. Yeah, now we've got 5 choices over here. Right? There's 5 choices. It can be anything but 4. 1, 2, 3, 4, 5. And we can pick something like 2, let's say. Now, what about the middle digit? How many choices for the middle digit? So the middle digit, there's no conditions other than the fact that all the digits are distinct. So it can't be the same as any of the already previously chosen digits. Right? So it can't be 2, 4, 7, 8, or 9. 2, 4, 7, 8, or 9. And our choices for these digits didn't matter because no matter what, there's going to be 5 digits that this 4th digit cannot be. So no matter what, because there's a total of 10 digits, 10 minus the 5 digits, it can't be, right? It can't be the same as any of the other digits. So 10 minus 5, 5 choices. And let's just say we pick 3 as our digit over here. So this is a valid number, but in total, the number of ways is 3 times 2 times 1 times 5 times 6 times 5. 3 times 2 times 1 is 6. 5 times 6 is 30 times 5. So 6 times 5, 30. So this is just 30 times 30, which is 900. So our answer, 900 for this interesting problem. Okay, now we're moving on to circular arrangements. So far you've been arranging objects in a line, right? We can have n factorial ways to arrange n objects in a line. But what if it was a circle? Then it turns out it's going to be n minus 1 factorial. Why? Well, take a look here. Let's say we have a, if rotations don't matter, it's going to be n minus 1 factorial. Let's say we have 5 people in a circle. So you would think it's just 5 factorial. But if rotations don't matter, then all the cases where somebody different is at this top position over here. We could rotate it so that E is now on top, and then it's E, A, B, C, D. Or we could rotate it so that D was on top, so then it's D, E, A, B, C. The point is, this letter over here, it can be anything. And 5 factorial would be counting these arrangements as all different, even though they're the same, rotated. So what we have to do is divide by 5, because there's 5 different ways that we can rotate the 5 people in the circle. And that's where we get this n minus 1 factorial term. In this case, it was 4 factorial, but if we have n objects or people or whatever else, n minus 1 factorial. And sometimes the problem might say that reflections are not the same. And if that's the case, then n minus 1 factorial divided by 2, because there's just 2 ways to reflect something like that. Let's take an interesting example that uses this. How many ways are there to arrange 5 people around a circle such that 2 of the people, Alex and Bob, must sit next to each other? So rotations are not counted as distinct orientations. So let's say we've got 5 different slots like this. Alex and Bob must sit next to each other. Let's say our 5 people are Alex, Bob, and then 3 other people we're going to call C, D, and E. Okay? So the strategy for doing what we did earlier is just to assume, let's say, one person's at the top. So over here, we can just assume that, let's say, A is fixed at the top position. And then there's 4 factorial ways to arrange the remaining people. That's one way to think about it as well. So let's try a similar idea to this in our problem. Let's assume A is at the top. And we can do this because if A was here, for example, we can just say it's the same arrangement, rotated. So A is at the top, and Alex and Bob must sit next to each other. So where can Bob be? Can Bob be here? No. Can Bob be here? No. Can Bob be here? Yes. Can Bob be here? Yes. So Bob essentially can be here or here, one of these two positions. If it was here, then how many ways are left? Well, now we've got 3 remaining people, C, D, and E. So 3 factorial ways to arrange those 3 people, right? It's just arranging 3 people. We've got 3 choices for this position, then 2 choices for this position, then 1 choice for this position. 3 factorial. Now, what if B was here? On the right. Now, there's again 3 slots remaining. Again, C, D, and E, there's 3 choices for this position, 3 choices for this position, 2 choices for this position, and 1 choice for this position. So again, plus 3 factorial. So if B is on the left, 3 factorial. B on the right, 3 factorial as well. Total, there's just 3 factorial plus 3 factorial. That's 6 plus 6 equals 12. Our answer is 12. Now you can get many practice problems here in the Mastering AMC book, but now we're going to move on to combinations. Combinations is where the order does not matter. And we'll be covering how to solve combinations problem in the next video over here.